Battery electric vehicles currently occupy the vast majority of the consumer market for zero-emission transport. While these cars handle urban mobility, several global powers are simultaneously deploying billions of dollars to establish a parallel transportation infrastructure based on hydrogen fuel cells. This split-screen visualization illustrates the core thermodynamic trade-off. On the left, battery electric vehicles possess a significant efficiency advantage, converting 90% of grid power into torque at the wheels. However, the map reveals a sharp geographical divergence. While Western markets prioritize battery passenger cars, Eastern economies, particularly China, are building massive hydrogen freight corridors to power their heavy industrial fleets. Heavy shipping and long-haul logistics are classified as hard-to-abate sectors. The lithium-ion systems that power a 3-ton commuter car do not scale efficiently when applied to the mass and continuous duty cycles required by industrial freight. For heavy-duty applications, the mass of the batteries required to move freight over long distances creates a diminishing return on energy. In these sectors, the physical constraints of weight and range require a different method of energy storage. Decarbonizing the global economy relies on a dual architecture ecosystem. No single hardware class can handle every sector of modern mobility. This fuel cell stack houses a series of vertical layers where an electrochemical reaction occurs. Highly pressurized hydrogen gas and ambient oxygen react across a platinum-coated membrane, producing a direct flow of electrons to drive a motor. The only byproduct is pure water vapor. This powertrain energy flow chart maps the efficiency cost of that reaction. Because creating hydrogen is a multi-stage process involving electrolysis, compression, and membrane conversion, it extracts less kinetic energy from a grid watt than a direct charging battery. But thermodynamic conversion is only one metric. We use life cycle assessment to track total emissions across a 10-year operational cycle, accounting for the carbon footprint of manufacturing and the impact of hardware degradation. Data from the ReCP 2016 framework shows that fuel cell commercial vehicles generate 12.36% lower cumulative greenhouse gases over their lifespan. During the operational phase specifically, hydrogen vehicles achieve a 53.51% emissions reduction compared to heavy battery tracks. These figures are a result of material durability. While the large lithium and cobalt batteries in heavy trucks suffer from the embodied carbon of mining and degradation from fast charging, hydrogen fuel cell plates maintain their performance over millions of miles. Efficiency at the plug matters less if the hardware itself requires carbon-intensive replacement due to the high wear cycles of commercial logistics. In long-haul logistics, energy storage density dictates the profitability of the route. Every kilogram of fuel system weight is a kilogram of freight that cannot be carried. This animation shows the gravimetric limit of lithium-ion batteries. To move a truck over long distances, the battery mass must increase significantly. That weight eventually consumes the legal limit of the vehicle, causing the profitable payload capacity to drop. Hydrogen bypasses this mass penalty. Utilizing a fuel cell and lightweight tanks allows the vehicle to carry energy in a much smaller physical footprint, preserving the truck's capacity for commercial freight. This hardware transition is currently facing obstacles. Daimler Trucks recently delayed the rollout of their hydrogen systems, citing the lack of specialized refueling infrastructure needed to support a commercial fleet. Other manufacturers are utilizing bridge technologies. Volvo's high-pressure direct injection engine burns hydrogen gas inside a traditional combustion block, allowing fleets to lower emissions while maintaining their existing mechanical systems. Because commercial transport operates on thin margins, heavy batteries represent an economic liability that many logistics networks cannot adopt. The global hydrogen map is characterized by asymmetry, with different regions applying the technology based on their specific infrastructure and state policies. Japan and Korea focus their national roadmaps on the passenger retail market, centering their strategy on millions of commuter vehicles like the Toyota Mirai. To address the scarcity of refueling stations, Honda engineered the CR-V-EF-CEV as a plug-in hybrid. It uses a lithium battery for daily urban driving, while keeping the fuel cell in reserve for long-distance routes. China follows a logistics-first strategy. They currently operate 95% of the world's hydrogen trucks, prioritizing the industrial supply chain over individual consumer cars. The United States presents a striking contradiction. Despite its technical capability, nearly all American retail hydrogen vehicles are confined within California, as refueling infrastructure is non-existent in other states. In Europe, the Hydrogen Mobility Europe project has integrated the technology across national borders, creating a synchronized network for commercial fleets and taxis. European network data shows a high level of operational reliability at 98.2%. For these drivers, filling the tank takes less than 5 minutes, providing an experience identical to using a gasoline pump. Superior engineering only matters when paired with synchronized state policy. Refueling infrastructure determines whether a vehicle class thrives or fails. Storing hydrogen in a vehicle requires overcoming its extreme lightness. The gas must be compressed to 700 bar, approximately 10,000 PSI, or cryogenically frozen into a liquid, just to achieve the necessary energy density. This dispenser represents a significant financial hurdle. Engineering a hydrogen refueling station costs up to 3 times more than a standard high-speed electric charger. These storage cylinders use a multi-layered defense system. The hydrogen is contained within an aerospace-grade carbon fiber core, which is protected by an outer glass fiber shield designed to show visible damage after a collision. While legacy gasoline tanks are made of relatively thin metal, hydrogen storage tanks are engineered to survive ballistic-level impacts and extreme temperatures without a breach in pressure. While the fuel cell vehicle is a mature technology, the station architecture required to support it remains the primary barrier to global adoption. This dual-axis graph shows the current economic gap. Retail hydrogen currently costs $32.94 per kilogram. To reach the parity line where hydrogen can compete with battery electric costs, that price must drop to $5.88. This translates to a high operational cost. Moving a bar 100 kilometers on hydrogen currently costs $11.40, while a residential battery charge for the same distance costs only $3. Closing this chasm requires shifting the supply chain. New electrolyzer designs are replacing expensive platinum and iridium with common transition metals, allowing hydrogen production to scale at a lower capital cost. Localized production also lowers costs. Indonesia is pursuing this through its 2060 roadmap, utilizing its geothermal energy to power clean hydrogen production on site. In West Java, a project led by Pertamina and Hyundai is converting landfill biogas into hydrogen. By producing fuel directly at the source, they eliminate the high costs associated with transporting the gas through a regional grid. Liquid organic hydrogen carriers offer a final solution for long-distance transport. By bonding the gas to a synthetic oil, hydrogen can be shipped at room temperature using standard industrial containers, removing the need for high-pressure or cryogenic shipping. Achieving the target cost of $1 per kilogram depends on these invisible supply chain shifts. Moving hydrogen as a stable liquid eliminates the massive investment required for a global network of cryogenic pipelines. The global energy transition utilizes 2 distinct classes of hardware, each engineered for a specific physical environment. This map of an urban grid shows why battery electric vehicles are the standard for light-duty transport. Residential charging and high thermodynamic efficiency make them the most effective choice for local commuter networks. Zooming out to a global scale reveals the sectors where hydrogen operates. Massive intercontinental shipping lanes and heavy industrial corridors require levels of power and energy density that lithium-ion technology cannot support. Industrial transport relies on energy systems that preserve payload, resist degradation, and allow for rapid refueling over millions of miles. Hydrogen acts as the mechanism for decoupling heavy industry from fossil fuels, addressing the massive sectors where battery physics reach their limit.